Hi, and welcome to this short concept bite introducing you to the equilibrium constant K. I have used the term equilibrium numerous times already in this course, in particular for thermodynamic equilibrium in phase changes, but so far I've never defined this important concept. If we initially just consider a simple system of a weak acid which can dissociate into a proton and a conjugate base, then there exists in solution a mixture of undissociated acid, protons and conjugated base. If I add more of one of these components, the reaction will proceed to restore the original equilibrium. But what is this equilibrium? Well, we define the equilibrium constant of a process or reaction as the activity of the products raised to their stoichiometric amounts divided by the activity of the reactants raised to their stoichiometric amounts. Equilibrium constants are defined against activity of reactants and products in part because activity is dimensionless and I can take a log of a dimensionless quantity. I cannot take the log of any quantity with units. The equilibrium constant is related to the driving force of the reaction by use of a log. Delta G is equal to minus RT log K. We can therefore see that the only thing that will affect the equilibrium constant for a given reaction is the temperature. Remember, as always, this is the thermodynamic temperature in Kelvin. Other versions of the equilibrium constant exist, but are often accompanied by a unit and therefore aren't practically used in thermodynamics. You will recall activity from elsewhere, and assuming the activity coefficient is 1, which is reasonable for gases at atmospheric pressure or low concentrations of non-charged species, the numerical value of activity and pressure or concentration are the same. However, ionic solutions deviate from ideality even at low concentration, and so activity has to be determined from the activity coefficient. You will likely already have met Le Châtelier's principle, which states, if a change is made to a system in dynamic equilibrium, the system will respond so as to oppose the change. What does this mean practically? Well, the only thing that can change the equilibrium constant K is the temperature. So in all other cases, any changes we make will actually cause the activity of reactants and products to adjust such that the equilibrium constant is unchanged. We have seen the equilibrium constant, which is related to activity of reactants and products at equilibrium, but there is an equivalent value called the reaction quotient, Q. The reaction quotient is defined as the activity of products raised to their stoichiometric amount divided by the activity of reactants raised to their stoichiometric amount at any point in the reaction. This means that we can also calculate the driving force at any point in the reaction by knowing the reaction quotient and the Gibbs free energy of reaction for pure reactants and pure products. When we are at equilibrium, RT log Q reduces to RT log K and the driving force of the reaction is 0. All reactions reach an equilibrium, even if that equilibrium lies incredibly close to either pure reactants or products. And the only thing that affects the equilibrium constant for a reaction is the temperature. Catalysts may make reactions come to equilibrium quicker, but they do not affect the position of the equilibrium. Further, we can determine the free energy at any point in a reaction by knowing the Gibbs free energy of pure reactants and products and the composition of reactants and products at that point. I hope that this video has helped you understand what is meant by both the equilibrium constant and reaction quotient. As always, if you have any questions, please do not hesitate to ask.